Hello, everybody. My name is Zhang and I'm from Zhejiang University. It's honor to be here to present my research on the numerical study on the urban thermal and wind environment. So it's a great pleasure for me to take this present this research because I'm after the Dr. Clement. So actually, before I come to here, I think I'm the second one after the Professor Clement. But actually, but I am the first one. So I don't know. Maybe the guy just the wrong way. Okay. So uh, let's address our first question. Why do we consider the urban heat island circulation? Urbanization is characterized by rapid expansion, um, altering the underlying surface property. Calm and stable conditions often lead to extreme heat rivers and urban heat island circulation, which is not only increase the surface temperature, but also create more serious pollution. And it's important to study the urban heat dome flow or urban heat island circulation. So how to visualize urban heat island circulation or heat dome flow. Under stable and calm background conditions, the airflow in the city is dominated by different scales of nature convection, and an urban heat dome flow form at the whole city scale. So there are two crucial factors for us to predict the urban heat dome flow. The one is zero background wind. Second one is thermal inversion layer or the background temperature stratification. We can see this. Um, so in our study, the approach is to extend the safety method to the mesoscale flues. Uh, we made some changes to set up equations to make it couple to the traditional CFD method. These changes include add some volume sources such as Korean audience terms, implement the buoyancy effect, and add some rewriting the energy equations to add the background temperature certification. A previous study have showing some characteristics of the urban heat dome flow. For a secure city, both the inflow at the low level and the outflow at the upper level are asymmetry. For a square city, however, no uniform flow pattern was observed with for diagonal inflow at the low level and for side outflow at the upper level. Also, the urban heat dome flow is periodic, and as seen or described by the previous studies, the urban heat dome flow just like a jellyfish and moving jellyfish. So it's maybe very interesting. As I mentioned before, the heat dome flow under a square city is non uniform. So capturing the flow under the square city may be very challenging. So at the first our research is on a square city. Also, the result of simulation results are compared with water tanker experiments. The results showed that the numerical model is in good agreement with the result obtained from the water tanker experiments. Also, as I mentioned before, the Korean audience term was added in the moment question. So the Korean audience effect is also considered in our study. Additionally, in order to save some competition time, we also create or designed a numerical rerouting water tank model. By using this model, it can successfully reproduce the diffusion effect in the real conditions. Uh, when the pre-audience effect is noticeable, both the inflow and upflow height showing the diffusion effect. And at the inflow height, the inflow is divided counterclockwise, and as upper level, divided airflow leaving the city center emerges gradually, and an anticlone is eventually seen. And also, we use this model to study the flows on the different city shapes. And you can see some structure above the different city shapes. All of the cases on before are studied under the conditions with no wind, but we all know the background flow speed and wind direction plays crucial roles in interacting with the urban heat dome flow. Uh, when there is a certain speed, the urban heat dome flow transform into a plume-like flow, and its structure will be significantly altered as the wind speed increases. Also, in order to enhance the ability our research, so we designed a stratified flow water tank. Uh, it contains It contains salter stratification systems, the flow generation systems, and uh, PRV test system. With the help of the stratified flow water tank, we can achieve a small flow under the stable stations. Also, with the help of the PRV system, we can capture the urban heated dome flow structures on the different height with the effect of the inflow speed. And more cases are studied now, so we can get more, maybe more result to get average velocity field. So let's include my presentation. Thank you.